as you can see, my talk is about ways to prevent ships from poisoning water. And the first question is, are the ships really poisoning our water? And the answer is, unfortunately, yes. And the reason is to prevent the ships from being coated with biofouling. So biofouling is defined as the adsorption of biological substances and life forms on artificial structures. And when you have lots of plants or mussels growing on your ship, the ship is slowed down by up to 89%, which causes nearly 90% addition by biofouling. So, and biofouling occurs not only in salt water but also in fresh water, so it is also an issue of any city related to a river, like here in Harbin. And so here I funded a clean and a biofoul ship to make it easier to visualize that when you have a whole zoo of large plants and mussels and bacterial slime below your ship, it is affecting the probability and the movement of the ship. So, unfortunately, I don't have a big harbor and ships in my laboratory, so I must go with smaller samples, and I try to prevent biofouling directly from the start. I try to prevent the spores and life forms from attaching to the surface. So here you can see a clean surface, and here some biofoul surface. So here you can see bacterial slime, a plant spore, and some remains of a dead worm. So it is quite difficult to prevent the attachment of so many different kinds of life forms. So, and I also have a video of some bacterial slime that you can see what is sticking on the ships. So here are some worms eating some bacteria, some plant spores, how to see, and lots of different kinds of bacteria. So, yeah, in the past, the scientists therefore decided to simply poison everything at the same time. So they simply put lots of dangerous chemicals on the hull of the ship and let the coating dissolve over a time scale of 5 years to have a constant release of poison to kill the life forms. And then the several governments forbidden these poisonous coatings, and the industry was quite clever. They simply exchanged the poisonous material with other poisonous material. So the problem remains until now. And most of the workers coating these ships are Chinese. So it is most interesting for this country here. And here on this scheme you can see how today's anti-biofouling coatings are working. So you have some kind of life form, a mussel larva, plant spore or bacteria trying to settle on a surface, and it is poisoned and then washed away either due to shear force or due to the dissolution of the coating. And when the coating dissolves itself over a large time scale, then all of the poisonous chemicals are in water, and yeah, the chemicals get accumulated in fish, and we humans are eating the fish. So, yeah, I was sitting down and trying to come up with some ideas what the ideal coating should do and how it should be. And my first idea was to prevent it from poisoning our water. Then my second idea was that it should be cheap. When it's too expensive, nobody can buy it. It should reduce the drag of the ship additionally, protect the ship from corrosion, and it should also be easy to apply. If nobody can do it, only some scientists, then it's not useful. And it should also last a long time. So then I looked into literature, what kind of material I should use, and in literature they stated that the surface organisms need hard surface, which is understandable because they attach to surfaces because they don't want to float around anymore. And so they hate soft surfaces, and commercial silicone rubber, everybody knows this material. In my home country we use it for ceiling windows, showed quite good properties. So it's a very soft material, so the life forms didn't like it. So then I came up with the idea, why not using a pan coating? It works for my food in the kitchen, so why it shouldn't prevent some other material to stick on it. So some other people already did it as well. So they showed that plants like pan coating surfaces, so they like to stick on it. And again, silicone rubber was the best, while commercial navy coatings, when you remove the poison, they are really loved by mussels and other larvae, so they could turn ships into moving mussel farms if they wouldn't contain so much poison. So so here you can see some common silicone rubber applied in every household, and in my laboratory we simply have a transparent and more soft version of it. And so if you coat a ship with this silicone rubber, it still gets fouled, so there are still some plants and animals attaching, but in contrast to current coatings, when the ship moves, these life forms are simply removed. So this is why this silicone rubber material is also called a folding release coating. So this test was not done by me, it was done by some other people. And so this approach is very useful for ships that move a lot and move fast, but it's not good for permanent structures. So buoys will still get fouled and lose their functionality. And so I thought, when we have a half-poisoned water, it's still not a clean water. So I tried to find some ways for buoys and the piers, and I need to say this research topic is still under investigation, so it's not finished. So, but there are some useful results until now, and they're quite nice. So then you put a structure onto the silicone rubber, and the structure is smaller than the animal will still settle, but when the structure is approximately half the size of the animal, then the life form will not settle on it. So you can imagine when you try to lie on a bed and the bed only covers half of your body, it is very uncomfortable and you try to get up as early as possible. And whereas when the structure is larger than the animal, it will feel protected and it will preferably settle on the surface. So this research was also done by some other people, but now here my research starts kicking in. So there's a big problem with this surface area minimization until now, because every biofoulant has a different size. So mussel larvae are around 100 times bigger than bacteria, and if you want to prevent bacteria and larva settlement at the same time, you need to have a structure on top of a structure, which is called superstructure. And so, I first tried to create a big structure with my laser printer, and I printed on a commercial overhead foil. And the printer that I used was not so good. So, because the printer had lots of defects. So, by accident, I created a quite useful structure on a structure when I just wanted to create a large structure. So I'm quite happy about this. And
PDMS is a silicone rubber, similar to the one used in every household for sealing windows. And the reason why this material is used for sealing windows is because it is very stable for the environment. And that's also why we use it in our experiment, because it is very, very stable for the environment and therefore long-lasting also in a water environment. And here you can see how we mix our laboratory grade. silicone rubber. We measured here around 10 milliliters, and here we are now pouring in a second component which is used for cross-linking our silicone rubber, and we use a 10:1 ratio. And after putting both components together, we are mixing it with a glass rod, as you can see here. And after very careful mixing both components, this material is poured onto our structured samples, or for structuring one can simply use a conventional foil for a laser printer and print a strict structure on it with a laser printer, or use a already prepared silicone master with some structure. So and it is very easy. This material can simply be poured onto the structure. So the hardening of this material takes a long time, and quite often also requires application of low pressure to remove the air bubbles, which can be clearly seen inside. And so, since this takes a while, we have already prepared a sample, and it can be clearly seen that the structure is transmitted from the master to the PDMS.
So I think it was not so clearly to see here. At least I didn't see the structure, so that's why here it's better to see that. So in this microscopic image you can see here's a large structure which can prevent the settlement from muscles on the surface, and there are small points which are due to the superstructure, and these small points prevent the settlement from smaller life forms like plant spores. And I need to say this research is not finished until now, so there are good intermediate results, but we want to make a more or less perfect surface. So within the next years there will be a big step forward on this kind of research. So here you can also see a 3D image. The structure that on the surface is really in 3D space and makes it very uncomfortable for the life forms to settle on it. So I hope that within the next few years most of the poisonous coatings can be replaced by such a material, and then we have clean water for everyone. Thank you very much. Are there any questions?